Hello, dear colleagues. My name is Daria, and I am with the Novosibirsk State Technical University. Our scientific team works on objectivization of the voice signals, and it's no secret that your voice can help identify a lot of things about your gender, age, sex, emotions, some health issues, psycho-emotional state, and others. And of course, currently we have a set of algorithms that have quite high precision in identifying and quantifying different characteristics of a person based on the voice. But our group was tasked with the research of voice parameters that have to do with some dysfunctions, both of the voice and of the specific voice organs. Recently, all over the world and in our country, we see a lot of people suffering from voice disorders. And first of all, these are illnesses that have to do with the voice dysfunctions. If, for example, the patient comes to the doctor complaining about the some fillings in the area of the neck, then the doctor, by seeing some organic damage on the voice cords, like tumors or some other things, they are easy to diagnose, and there are methodics that help you solve those. And separately, there's a class of illnesses that have to do with the voice itself, that are not caused by the dysfunctions in the voice cords, but the changes of the voice that have to do with the resonators themselves. The reason for those dysfunctions are usually psycho-emotional stresses that lead to the person using the voice apparatus wrongly. This can lead to very dire consequences and actually create organic damage to the voice cords and lead to the loss of voice, or even create psycho-emotional stress. So it's important to diagnose the dysfunctions, voice dysfunctions early, and you need to have high accuracy of that recognition, and effective voice therapy is important, because the voice dysfunctions are not usually cured by some pills. They are cured by voice exercises and therapy. And of course, this is connected with the restoration of the psycho-emotional state itself. Currently, in Russia, there is usually only urgent ways of finding out what's wrong with you, when a phoniator or a therapist would just listen to what's going on and assess the disorder and its severeness. Of course, those methods cannot be systemized and used for proper voice therapy. That is why one of our main tasks was to create a system for processing the voice signal that would enable, just by using your voice, to find out whether there's some dysfunctions and ensure we assess the severity of the dysfunction. We've received and came up with that algorithm that, besides just the diagnostics, can be a way to create a biological feedback loop to not only diagnose, but also carry out the therapy. So what is the foundation of our method? Voice dysfunctions usually have a lot to do with the resonators, and resonators are just cavities in front of the sound source that are the nasal, the oral, and other cavities. And if something is wrong with the voice, then it means that the resonators work in an incorrect way, and our voice has some subharmonics or wrong overtones, that, as they call it in music or in singing. On this slide, you can see what I mean by those subharmonics. On the left, you have an audiogram and the spectre of the original sound. Let's say it's a sound, and its soundtrack. After that, this signal with one dominant frequency leaves the mouth of a person, then it goes through, leaves the vocal cords, and then after passing through the vocal tract, both the audiogram and the form of the signal, and of course the spectral picture, differs a lot. Here you see those two peaks, meaning that there is a separate area of amplified harmonics. And those spectrums are researched by our team because those obertones carry a lot of information about potential dysfunctions in your voice. So what did we get? Well, first of all, to begin with, we had a look at how this task is performed by the current algorithms for voice processing. Work with this. We took the groups of from the International Group and Voice database and calculated the standard parameters for acoustic voice analysis. And we saw here that besides just only the normal voices having nominal distribution, we see that the dysfunctions lead to a huge spread of parameters, and those parameters are so variable, so much spread, that they cannot be objectively used for diagnostics. Also, we have kids, for example, who have different spectral picture, and the parameters we calculated did not show any prognostic value to predict dysphonia or other dysfunctions. This has led us to create a very much needed algorithm that I'm going to present now. we offer it, and it's aimed at automatic recognition of voice dysfunctions. We would like to focus our research in a stationary section on the open A sound, because it's the most illustrative and the most universal in terms of its usage in different voice groups, language groups. So we find a stationary part and define the frequency, fundamental frequency of the voice chords. And then we conduct a Fourier transformation that gives us the spectrum of the signal. The spectra themselves can give us information about whether the voice is in the normal state or there's some deviation. On the 96,000 reports, we found very different results with a huge distribution. But on the left, you would see normal A spectrum, and to the right, the deviation with different maximal values for different harmonics. Then we calculate the using the special algorithm the amplitudes for all the harmonics, and as an interesting thing here is that we normalize not the formatted areas but the ones that are specific to each and every harmonic out of the first 7. And comparing the energy impact of each harmonic into the signal, we compare those examples with the control group and experimental group. This slide shows the results for this algorithm working on 2 groups, the experimental one and the control one. Each group had 30 people with either absence of dysfunction or where the functional the dysfunctions were maximal. So the difference between the values in the harmonics is very high. It's especially true for the first, the second, and the fourth. And the probability of error is less than 5%. So to conduct a detailed analysis, we have run this algorithm for different groups before and after the voice therapy. We chose 9 children with functional disorders. We've recorded their voices, same with the open A, and calculated the first, second, and the fourth harmonics. The data you see on the diagrams to the left. The chosen group of people has undergone voice therapy lessons, and then we've recalculated the harmonics, and you see them on the diagrams to the right. The red area is usually the normalized normal values. So you see that this repetition of measurements shows all the values going exactly to the area from the first research. This means that this algorithm has such high quality of statistical analysis that it can be the basis for diagnosing the dysfunctions of voice, both for adults and children. And currently, with the amount of samples that we have, we can say that the accuracy is really very high. Given this, we think that this algorithm can be applied as a diagnostics tool for phoniatrics, phonopedics, musical schools, and other educational institutions. You can use it to find vocal dysfunctions with the kids on the early stages and with the grown-ups. With that, I would like to thank you for your attention, and I'm happy to answer all your questions.